Alright, let's take a front row seat to one of the universe's greatest origin stories. Step 1. Start with nothing special. Picture a gigantic, cold cloud of gas and dust, like a cosmic fog bank that's light years wide. It's mostly hydrogen, with a dash of helium. Tiny bits of heavier stuff from older stars. It just floats. Quiet. Dark. Waiting. Step 2. Stir the pot. A nearby supernova pops. Two clouds bump into each other, or gravity slowly wins a tiny tug of war. Somewhere inside that cloud, a patch gets just a little denser than the rest. That's all gravity needs. It starts pulling more gas in. Density attracts density. The patch shrinks. Pressure rises. The temperature creeps up. Step 3. The collapse begins. Now it's a race inward. The cloud fragment collapses under its own weight. It spins, because everything spins. As it spins, it flattens into a pancake, a swirling disk with a growing lump in the middle. That lump? That's the seed of a star. Step 4. Say hello to a protostar. In the center, gas piles up. The pressure squeezes the atoms. The temperature skyrockets. Thousands of degrees. Tens of thousands of degrees. The core glows from sheer heat. No nuclear fusion yet. Around it, the disk feeds the baby star like a cosmic conveyor belt. Step 5. Cosmic jets, because stars are dramatic. As the protostar gulps down more gas, magnetic fields twist and fling material away in narrow jets. Jets blasting above and below the disk. It's messy, loud, and beautiful, like birth usually is. Those jets clear space around the star and shape future planets in the disk. Step 6. The ignition point. There's a magic number here, about 10 million degrees in the core. When the protostar is massive enough, hot enough, and squeezed tightly enough, hydrogen nuclei finally start fusing into helium. Fusion lights up. This isn't just heat from gravity anymore. This is a core engine turning mass into energy. The star is officially born. Step 7. Balance. Gravity versus light. Every second, gravity tries to crush the star inward. Every second, fusion pushes outward with light and heat. When those two forces match, the star settles into the main sequence, a long, surprisingly stable middle age. This is where the sun lives. Step 8. What makes stars different sizes? If the collapsing clump isn't massive enough, below about 8% of the sun's mass, it never gets hot enough for full hydrogen fusion. It becomes a brown dwarf, too big to be a planet, too small to shine like a true star. Get more mass, and you get brighter, bluer stars that burn fast and die young. Less mass, and you get red, dim stars that sip their fuel and can outlive the universe. Step 9. Time is weird out here. A massive star can form in a few 100,000 years and blaze through its life in a few million. A small star can take tens of millions of years just to fully arrive, then live for trillions. Star time doesn't match ours. Step 10. The neighborhood matters. Stars rarely form alone. Those giant clouds can birth clusters, families of stars. Some stay bound together, some drift apart. Nearby, newborn stars can blast each other with radiation, sculpting disks, maybe even nudging where planets will form. Step 11. Why this matters to you and me. Everything you are, your bones, your blood, your phone, the air you breathe, comes from earlier stars that lived, fused, and exploded. Starbirth isn't just a cosmic event. It's chapter 1 of every story that follows. Quick recap. Cold cloud. Gravity seeds a dense core. Collapse and spin make a disk. Protostar heats up. Jets clear the scene. Core ignition lights fusion. Balance creates a stable star. Mass decides the star's fate. Next time you look up and see a pinpoint of light, remember, that's not just shining. It's balancing, burning, and becoming. Every star you see is the end of a long, invisible journey that began in the dark. And somewhere, right now, in a silent cloud far away, another one is starting.